Welcome to the course Mathematical Aspects of Biomedical Electronic System Design. Today we are going to cover the topic Tissue Electrode Interface. In different TS sessions across them, you might have been taught about how a particular tissue or a basic unit, rather cell, can be modeled in terms of electrical parameters such as resistor, capacitor, and how it can help us in understanding its physical property by modeling it in terms of such elements such as resistors or capacitors. Now, once you have understood how tissues or cells can be modeled in terms of electrical equivalent parameters, the next logical step rather would be to make use of the existing electrode technology using microfabrication methods, and then try to study what exactly is being measured when you put an electrode on top of a tissue. What are the properties that you can measure? Can you delineate between, for example, a normal tissue from a cancer tissue? So these are some interesting examples that we are going to study in coming few 30 minutes. So I have taken one example from a journal article. In this particular work, what they did was they created an electrode interface, and let's say this is a well. This is filled with PBS. PBS is phosphate, B is buffer, and S is saline. Phosphate buffer saline. It's a buffer solution used to maintain the pH value constant, and it is found to be compatible across most of the biological tissues which are used for such experiments. So the medium in which this tissue slice was placed was phosphate buffer solution, and then there were electrodes below this. As you can see here, these are the electrodes. These are gold electrodes, and then this was the tissue slice, and this is the PBS solution. Now you have been taught how to model a tissue slice, like it will have a conductive component constituted by extracellular, intracellular matrix, and how like a lipid layer can be modeled in terms of capacitor, and the extracellular membrane by a resistor, and the combination of both of them by a resistor and a capacitor. Similar thing we will take forward from there, like how this particular combination along with tissue can be used to develop or come up with an expression for the net impedance. Z net here is net impedance of tissue and electrode. So let us see. So let us begin with tissue. So tissue will contain a resistive element, extracellular matrix, and bilipid bilayer membrane that offers capacitive behavior. Apart from that, the PBS in which this entire tissue is placed will provide another resistance. Now if you can see here, this PBS surrounds the tissue, like you can imagine it to be a well. Like this is a well in which this is PBS filled well, and somewhere here the tissue slice is kept. The shaded region that you see here is the tissue slice, and below the tissue slice there are metal electrodes. Metal electrodes which are connected to a power supply and a measuring unit. Yeah. Now what we can see from here is the resistance offered by the PBS, if this is the resistor, I can draw it here, and the resistor capacitor combination, which I will draw here. If you see this together, you can easily make it out that these two are in parallel combination. And that is why, if you can see here, this particular part is tissue electrical equivalent, and this is the PBS that is considered to be in parallel with the tissue. Now the second interesting thing is the CDL. Now let us understand what does this CDL means. And why there are two CDL elements which are capacitive. What do they mean? What is their significance? And how it can affect the measurements, especially bioimpedance measurements. So all these measurements which involve measuring impedivity, resistivity, it's called bioimpedance measurement. So what is this CDL? CDL is double layer capacitor or a double layer capacitor. Now what is this double layer? DL stands for double layer. So this double layer is constituted by the electrode and the tissue. So if you can see here, this part and this interface, if you see, this part and this interface, if you see, this entire thing is called double layer. I will draw the same here. These two are double layers. Now what is their significance? This provides the information that how much is the impedance between the tissue, the contact impedance, and electrode. And this can affect the measurement to a great extent. Let us say you do not have a proper contact. When I say contact, I mean electrical contact. When you do not have electrical contact between tissue and the electrode, what would it mean? It would mean that this value will be very high, because there will be lot of parasitic elements which will mostly be capacitor, that will lead to very high overall impedance. Now that overall impedance we will come to in the next few minutes, but for now, for your understanding, this concept just is to signify the importance of CDL, which is double layer or capacitor, which is found between tissue and the electrode interface. Now let us look at the overall circuit and how the expression develops. So as we can see here, the Z net, which is the net impedance, which I had mentioned earlier. So Z net will be given by reactance of the double layer. So this is the reactance of the double layer. Since it is a capacitor, it will just have a reactance, and then you will have in addition this entire thing, will be in series with this double layer. So that is why this is your caused by CDL, this is your tissue plus PBS, and this is again CDL. So now are you able to imagine it again? The elements, let us have a look at it again. XDL corresponds to the reactance offered by this capacitor, which is double layer, which is between electrode and tissue. This expression, which is resistance offered by PBS, phosphate buffer saline solution, which is in parallel with the ZT. ZT is tissue impedance. tissue impedance. And Zt is given by a parallel combination of RT and CT. And then again there will be another XDL because tissue is contacted by the electrode on two sides. This is one side, this is another side. So it can, if I were to draw the resistor capacitor combination here, it would look something like this. Just for your better understanding, you will have a resistor and a capacitor parallel combination. Here will be a resistor and then there will be a capacitor. This will be CDL, CDL, this will be RT, this will be CT, and this will be our PBS. So till this point it is clear. So now what you will do, you will substitute the values individually for each of these components. Let us begin with the first one, XDL. XDL will be given by, what is the expression for any capacitor? 1 over 2 pi Fc, right? Or 1 over j omega c. In a similar way we can write here XDL is equal to 1 over j 2 pi f, which is omega, and CDL, which is the double layer capacitor, which again I am emphasizing the fact again that it is formed due to the electrode tissue interface. Now ZT. ZT is impedance, overall impedance of the tissue. This is overall impedance of the tissue by itself. It is not in contact with the electrode. That's why I am just trying to make things clear in terms of electrode tissue interface impedance and tissue impedance alone. There are two things. One is electrode tissue impedance, which is CDL here, and there is tissue impedance, which can be given by RT, since these two are in parallel. So once you have a parallel RC combination, what will be? It will be R over 1 plus j omega RC. This is what it is written here. R over 1 plus 2 pi f is omega, R, C and j. This expression is clear, this expression is clear. Now let us substitute these two expressions in, let's call it this equation 1. So when we substitute this in equation 1, what do we get? We get Z net equal to 1 over 2 pi f CDL plus, this will be the parallel combination between RPBS plus ZT. This is by 2 CDL, one on this part and one on this side, okay? And then there will be this central element, which is a parallel combination of resistance offered by PBS and ZT. What you get finally is RPBS in parallel with RT over 1 plus j 2 pi RF. This again is omega RT CT. This is the expression that we have put here, and this is the expression which we have put here. So this was one of the examples just to demonstrate how you can measure or how you can come up with an expression. This is the simplest model. This is a simple lumped model. What do I mean by that? We are not taking any distributed element. Distributed element means capacitance per length, per unit length. Why are we not going for this? Because the length of the overall experimental setup does not warrant us to go for this kind of distributed element, which is generally used in transmission lines. Transmission line, mostly electrical engineers or electronics engineers would know. Others don't need to bother about it. For others, this is a lumped model, lumped circuit element model, lumped equivalent circuit model. Okay. So we have seen a type of tissue, which is the breast tissue here. So this breast tissue was excised after, let's say, a procedure of biopsy, and then it was stored in formalin, and then it was brought to a lab and then it was measured. This type of experiments are called ex vivo, wherein you are bringing in the tissue somewhere in the lab setup and then you are measuring it with your experimental setup. Now let us see, if you want to measure in vivo, which means you have your device which is portable and it can be taken to any place in any hospital setup, and then you want to measure the impedance or potentials. Now many of you would wonder how we can measure potential from tissues. We supply potential and then we can measure the impedance. Till now that has been our general understanding. In the next slide we will see how we can measure potential from a tissue. So what kind of tissues generate potential? That is the first question one should ask. So the kind of tissues that generate potentials form the most important part of our body, which is brain. And the tissues which are associated with brain are neural tissues. And the simplest unit of neural tissue is neuron. So this example, wherein you can see this is an example of neuron. So neuronal tissues generate potentials. I will not go into the details of the biology over there. That will be another session in itself. So neuronal tissues generate potentials, and a single neuronal potential is called as action potential. It's called as action potential. And when many such neurons, imagine there are millions and millions of neurons in our brain. So let's say when there are bunch of neurons, when they generate potentials across a large spatial domain, so let's say this is a particular part of a brain, and these lines are nothing but neurons. So each neuron is generating some potential. Collective potential of such neurons is local field potential. Or LFP. Those who are interested can read further about these two terms, but we will restrict our discussion only with reference to the context, which is electrode tissue interface and electrode tissue impedance. So let us see how electrode tissue interface exists for a neuronal tissue. How is this neuronal tissue different than the breast tissue that we had discussed? It is different in two ways. This part of the discussion is different in two ways. One, here we are talking about in vivo. In vivo means we are taking the device or the sensor and we are placing inside the body, in this case inside the brain. So the standard operating procedure would be to perform a surgery and then create an opening and then expose the cortical surface. And the signals that you will record from a cortical surface, electrical signals that you will record, also called neural recording from a cortical surface, is called ECOG or electrocorticography. So let us see what all different elements are there as far as recording of neural signals is concerned. So this is the probe that you have implanted on the cortical surface, and the signal which is being recorded will be sent to a signal conditioning circuit. So let us see each element individually. Let us begin with the neural tissue. As I had mentioned, each neuron generates some potential which is called action potential, and collective collective firing of neurons generates local field potentials. So this can be considered as potentials generated by neurons. This is neuronal potential. Then there will be something called as R spread. So this is associated with extracellular space. So in some other TA classes you definitely would have been taught about intracellular and extracellular, and extracellular is generally associated with resistive contribution in terms of electrical equivalent. So this is extracellular space in cortical surface. Now this is where it comes the interesting part. This again is the interface between electrode and neuronal tissue. This CE again will be double layer capacitance. Remember the double layer capacitance that we had talked about for the breast tissue. So in case of breast tissue too, in the previous slide we had talked about electrodes, and on top of that there was a slice of tissue, and this part, the impedance offered by this was CDL. In a similar way, just the name is changed, the concept remains the same. This is CE or double layer capacitance. RE is the leakage resistance. So like you have leakage capacitor at the contact, similar way you have leakage resistor. And finally you will have RS. RS is nothing but interconnect resistance. So just to give you an idea what exactly would this system would look like. So imagine this to be the cortical surface and this to be the electrode. So the shaded region is the electrode, and then this is connected, let's say this is a ground point, and both of them are connected to a voltmeter. This is a very simplistic view. The electronics associated with neuropotentials recording is very complex because of several reasons which is out of the scope of this particular TA session. So this electrode, let's say it consists of recording sites and then interconnects which are then connected to this, recording system. So this shaded area is the part where these things come, and this part which is the interconnect is RS. So this electrode, this recording electrode, when it comes in contact with the tissue, I am drawing the tissue for simplicity in the form of a square, this will form the CE and RE component, electrical equivalent CE and RE, and RS will be the interconnect of this electrode, neural recording electrode. So this was just to give you an idea that how electrode tissue interface can not only mean you are supplying the potential and then measuring the impedance, but it can be the other way, you are measuring potentials, and there are several applications for measuring neuronal potentials. It can be used to understand several neurological disorders such as epilepsy, stroke. In a similar way, this kind of interface can also be drawn for neural stimulation, wherein here you are recording, there you are stimulating, current pulses. In that case also you can work out for electrical equivalents when a particular electrode comes in contact with a neuronal tissue. Now one more important aspect which we thought of bringing out in this TA session was that what are the factors that affect electrode tissue interface and how those effects can be modeled. So these are some real time or practical issues which can help one in designing electrodes and also modeling the electrode tissue interface for understanding the potentials which are recorded, especially in this case for neural tissues. So we are seeing a case, there are two equivalent circuits drawn here. In one case you can see Z scar. Apart from that, all the other things were common as the previous case in which we had seen an electrode in contact with neuronal tissue for neural recording. So what does this Z scar mean? Whenever you insert any foreign object, the first response of our body is foreign body response. It is termed as foreign body response, or FBR. Now this FBR can also be in terms of neural tissue considered as neuroinflammatory response, which means if any foreign object is being inserted, in this case electrode, it causes inflammation or adverse effect to the tissue. It can cause breakage of the tissue, or it can cause blockage of the blood flow inside the brain. When such things happen, body has automated response wherein it will develop a protective coating around the electrode, and that is something called as fibrosis. I am not going into the detail. And that fibrosis will prevent any kind of signal being recorded accurately. It will offer an impedance, and this Z scar is the impedance offered by this particular phenomenon. In a similar way, this Z scar can also occur if you are having if there is a presence of blood in between the electrode and the tissue. So this Z scar can also be due to blood as well. Now then the question arises, is there any way to improve or improve this improve the overall electrode tissue interface? What does it mean? Reducing this quantity and eliminating this quantity. This quantity we cannot eliminate because by default electrode tissue are two different materials. There will be some double layer capacitance and some resistance, leakage resistance associated with that, but this Z scar is something that can be totally avoided. The one way to avoid that Z scar is to use electrodes which have very high surface area and have very high surface area. And second, low Young's modulus. So if an electrode has a very high surface area, what is the advantage it offers? It offers the advantage of making better contact with the neuronal tissue, because if you consider human brain, it is having gyrus and sulci, which means if you have seen human brain anywhere, either phantom or in pictures, it will have some kind of shape, something like this, undulations like this. Now if your electrode is sitting like this, let us say this is your electrode, the shaded region. Imagine the kind of electrode tissue interface that it will have for this case when compared to the case where electrode is conformable to the tissue. So what will be the difference? The signal to noise ratio will be very high in this case when compared to this case. Also, if you have a very stiff material acting as an electrode, it can cause, because body tissues have Young's modulus around 10 kilopascals. This is a very general value. For different kinds of tissues, these value can be even smaller or little higher, but these materials, let us say for example silicon, will have Young's modulus at least 3 to 4 orders of magnitude higher than this particular value. So what will it cause? It will cause scars, it will cause rupturing of neural tissues, which will result in processes like fibrosis or neuroinflammation, anti-inflammation processes. So what we were discussing is, if you have a very stiff material, when I say stiff, it is mechanically stiff, something like silicon, and if you place it on cortical tissues, and if you insert it, first of all, if you insert it and then place it on the cortical tissue, it can lead to adverse response from the, I would rather say preventive response from the body, which is called neuroinflammatory response or foreign body response, which can result in fibrosis, which can lead to coverage of the tissue with fibers, which are generated as a result of fibrosis. Contrary to that, if you have a material which is mechanically soft and has Young's modulus comparable to that of neural tissues around 10 kilopascals, then there will be two advantages. First, it will have low Young's modulus, and also the contact that it is making with the neural tissues will be better or improved when compared to such stiff materials, which will result in reduced value of double layer as well as leakage resistor. This can also be added with materials which are known to have very high surface to volume ratio, which is something like nanomaterials. So let us say you have carbon nanotubes or graphene. These materials have very high surface to volume ratio. So if these materials when combined with the mechanical softness of substrates like polymers can result in both of these parameters being satisfied, resulting in overall reduction in the impedance offered by tissue electrode interface, which in turn results in improved quality of the recorded signal. Now this brings us to the end of this session. What are the takeaways? Takeaways are as follows. 1. In order to model any kind of tissue electrode interface, you need to know what kind of resistors and capacitors are there. We took a case example of breast tissue, wherein there were two double layer which are capacitors on either side offered by tissue electrode interface, and the tissue impedance itself and the medium. Now remember, medium may or may not be there, you may or may not have PBS, so you do not have to follow it point to point. In fact, this is just a direction in which you can think about. In a second case, we took the example where you are not measuring impedance by supplying voltage, but you are recording potentials, which is the case for neural recording, and we saw what all elements are there in case of neural recording, wherein an electrode makes a contact with the neural tissues. Then we saw what are the factors in which electrode tissue interface, specifically we took the case for neural tissues, can get affected, and what are the methods that can be used to develop devices which can mitigate the issues raised by conventional materials or biological responses when conventional materials are inserted in in a brain and placed on a cortical surface. I hope this lecture helps you in improving your understanding on electrode tissue interface. Thank you so much for listening. If you have any doubts, please feel free to put up the questions on the forum. Thank you.